Hello my esteemed viewers. This tutorial will again discuss the problems that cover the aspects of normal stress, strain, shear strain, and the things related to the concept of what is called a simple stress and strain. The problems in this tutorial are sorted in the increasing order of complexity. Our esteemed viewers will recall that thus far we have clearly understood the concepts of simple stress and simple strain through 15 problems, and therefore we start from the 16th problem in this tutorial. The problem reads, a steel pipe having yield stress of sigma y 270 MPa is to carry an axial compressive load V equal to 1200 kilonewton. A factor of safety of 1.8 against yielding is to be used. If the thickness T of the pipe is to be 1/8 of its outer diameter, what is the minimum required outer diameter? That is D minimum. So this is about a hollow cylindrical component and a load is applied, and this is the cross-sectional configuration of this particular component. And anyway, we know any component, as a matter of fact, will not be designed for the yield stress. Therefore, we make use of the factor of safety to find out the allowable stress, working stress, or permissible stress, whatever we can say. And the component being hollow, the area of cross section happens to be pi, the outer circle, the area of the outer circle and area of the inner circle. And what remains if we minus the area of the outer circle with the inner circle, what we get is the material really available in the annular space. So it is pi d square minus, since the thickness is d by 8 and there are two thicknesses, one over here and one over here, and that will get us the inner diameter. Therefore inner diameter happens to be d minus 2d by 8 whole square divided by 4. So this reduces to 0.34 d square. And if we continue with the basic equation of stress equal to load by area, so stress happens to be the working stress, that is 150 Newton per millimeter square or 150 MPa, equal to the load applied is 1200 kilonewton. Therefore 1000 kilonewton, make it Newton by multiplying by 1000, and the area of cross section is down over here in the denominator, and upon simplifying we will get d square equal to this much, and when we take the square root out of it, we will find the diameter, the outer diameter, to be 153.4 millimeter. Now a solid bar of circular cross section diameter d has a hole of diameter d by 4 drilled. So if this is the diameter, there is a hole that is being driven in this particular component, and the diameter of that particular hole happens to be d by 4, that 1/4 of the main diameter, and laterally through the center of the bar. Calculate the value of P allowable if the bar is made out of brass with the diameter d equal to 40 millimeter, and sigma allowable value, it is sigma allowable value being that is 80 MPa. Okay, and yeah, P allowable, we need to find out the allowable load over here, and the diameter given to be 40 millimeter, and this is sigma allowable, this is equal to 80 MPa. So there we stand, and we will continue with the problem. So when the forces are pulled, and this will become a critical cross section, where because most of the area, most of the material is taken out by drilling a hole, and in the cross section it will look like this, particularly at this particular section. And if you take section elsewhere, full material is available. Therefore if at all failure is expected, it should be expected over here, and the true area of cross section will be reduced over here. Therefore we need to consider this particular we have to lessen the total area, the area of cross section of this particular rod minus the hole, and the hole will look like this. all through. It has started from over here, and it has entered. It is being driven through the entire component. Therefore, it is fully wide. It is fully wide. Therefore, sigma allowable equal to P allowable divided by A, and area of cross section is to be calculated something like this. This is pi d square by 4. This is the full circular area by 4 minus d into d by 4. Okay, it is d by 4. This is the this is the width, and this is d. Okay, this is the rectangular cross sectional area, which has become wide. Therefore, this is the net area that is available, or this is the area where material will be able to resist. It is not the total area, it is something lesser than the total area of cross section because of this hole. Therefore, sigma allowable, that is given to be 80 equal to P allowable divided by 856, and what we get is the P allowable in terms of Newton, and if we divide it by 1000, we will get a load in kilonewton. And this problem reads like this: axial loads are applied to the compound rod, that is composed of an aluminum segment rigidly connected between the steel and bronze segments. What is the stress in each material given P equal to 10 kilonewton? So this is a direct application of, as you must have guessed, this is a direct application of principle of superposition. Therefore, we come from this end, we will write the free body diagram of the each and every component, and we will just put up the load over there by considering the equilibrium of the entire segment. So we will take the first component. So anyway, we have to apply the principle of superposition. So we will take this first component that is made out of steel. Here there is 3p acting, so 3p over here. In order to keep regard of the equilibrium for this particular component piece that is made out of steel, there is a 3p, that is the load will be set up over here. So this 3p and this 3p will get cancelled away, and this particular component will be in equilibrium. So we apply this directly. 3p divided by A, area of cross section is given to us, and it happens to be this particular component of steel. The subcomponent of the steel is experiencing a stress of 100 MPa. In the same token, if we write the free body diagram of the other portion, that is the aluminium, from here it is 3p minus p, and we will regard 3p, the tensile forces, to be positive and compressive forces to be negative, and we will get 2p, that is tensile force acting over here. And therefore, in order to keep this component is also in equilibrium, 2p will be developed over here also, and area of cross section is given to us. We will directly apply, and we happen to see that the axial stress in aluminium portion happens to be 33.33 MPa. If we continue with the problem, and this is the bronze portion, and which is subjected to 4p, as you can see in the main diagram, it is 4p negative. Therefore, negative means compression, as we told. So 3p, which is positive, minus p in the other in the aluminum portion, minus 4p, which is acting at this particular junction. So the net force is minus 2p, and we have to regard this as a compressive force, and here exactly the force will be acting from this side. It should be minus 4p, it should be 2p. Anyway, something wrong has gone over here. Yeah, we will just change that. Sorry, it should be 2p. Yeah, we'll make it 2p. Yeah, this is 2p, and we will apply the load over here, and we will apply the simple formula. Anyway, this piece also subjected to simple stress, normal stress, 2p divided by A, and area of cross section is given to us. It is 50 MPa, and we can see from this formula, from this particular problem, though it is a component as a whole, the individual components made out of different materials, due to their different allowable stress levels, they are also experiencing different allowable stress levels. The calculated stress levels also happen to be different. Find the maximum allowable value of P for the column. The cross-sectional areas and working stress are shown in the figure. So this is a column. This portion is made out of steel, and this portion is made out of timber, and this portion is made out of concrete. Anyway, this is nothing, this is no longer this is no different from the previous problem, but anyway it comes with a question that we need to find out the most allowable value of the minimum allowable value of P. Therefore, once again we will start with the free body diagram of the steel component. It comes over here and we will apply 2P, and simply definitely a 2P should be developed in the opposite direction over here in order to keep this piece in equilibrium. So sigma steel is 2P by A, and we will get the value, everything is given to us. Therefore P happens to be 30 kilonewton. So as far as steel is concerned, it can take 30 kilonewton in order to keep the allowable stress limit of 120 Newton per millimeter square or 120 MPa. As far as timber is concerned, it is 2P minus P, and it will be P, and it will be P from the bottom. Therefore, even and if you apply the simple formula, we will get the stress, the load that can be taken by this timber portion, it happens to be 24 kilonewton. And if we come from the top, once again it is 2P for the top portion and minus P for this and plus 4P, because it is like this once again. And if you consider concrete, it is 2P minus P plus 4P. So that becomes 5P divided by A. Therefore the allowable permissible stress in concrete is given to be 16 MPa. So if you apply this, it's a straightforward problem anyway, but the points that is to be taken out from this problem is the lowest of the three values, that is 24 kilonewton, is to be selected. And if we apply 24 kilonewton as a value of P, even concrete will be safe, the timber portion will be safe, and the top portion of the material will also be safe. A compound bar, once again this is an example of the previous example, also is an example of a principle of superposition. A compound bar consisting of bronze, aluminum and steel, it is something like this, and the stress levels are given, area of cross section is given, elastic modulus of different materials are given, and working stress level is also given. And let us see the question. Determine the maximum allowable value of P if the change in length of the bar is limited to 2 mm and the working stress prescribed in the table are not exceeded. It comes as another example, as I told, but this is a little different as far as computation is concerned, because we need to find most appropriate value of P which can never cause net extension to exceed net deformation, whether it is extension or compression, should not exceed 2 mm, and the stress in all the components should be within their permissible limits. Therefore we need to choose, we have two criterions over here. One, the first criteria, the net deformation should be less than or equal to 2 mm, while the stresses should be within the limits as it is indicated for different materials out of which the entire component is being made. So we will just tackle this problem. So this is 2P, the first portion. We are coming from the right, and this is also 2P, and we find the change in length in steel. It is elongation because it is tension, happens to be 2.66 into 10 to the power of minus P in terms of P. And once again, as far as this is concerned, 2P positive minus 4P which is acting at this particular junction, which happens to be 2P, which is compression, because it becomes minus 2P. It is shown in the form of the sense, it is compressive force, and here again it is 2P in order to keep regard of the equilibrium. And if we apply the formula PL by AE, we will get the compression of aluminum portion to be 4.76 into 10 to the power of minus 5P, and it is shown in the form of negative sign, and here it is positive sign. Elongation is positive and compression is negative, that is our sign convention. And this is the bronze portion, and here P is acting, which is minus, which is compressive. So 2P from the other end minus 4P, which is applied over here at this particular junction, and minus P. This happens to be minus 3P, and 3P is acting over here. Even this piece is also subjected to compressive load. Therefore change in length in bronze happens to be minus 4.82 into 10 to the power of minus 5P, and we will add them together. we'll add them together. This is the elongation of the first piece, and this is the compression, that is the compression. This is the elongation, change in length, elongation, increase in length, decrease in length. This is also decrease in length, but anyway the net deformation should be equal to 2 because it should not exceed 2. And if we simplify this, we will come out with the value of P equal to 28.9 kilonewton. So if we consider the criteria of limiting the deformation to 2 millimeter, it comes to be 28.9 kilonewton. Let us see the other criterion. 2P by 300 equal to 140 because the limiting stress in bronze is given to be 120, aluminum is given to be 80, and steel is given to be 140. It is 140, and this is 80, and this is 120. So we will apply this. Stress is given, and we will find out the load out of it, the permissible load, and we will select the minimum as we did in the previous problem. So for P steel happens to be 21 kilonewton. For P aluminum it happens to be 24 kilonewton, and here this is substituted. This is the working stress for that particular material, and this happens to be 18 kilonewton. And among all the loads that we considered, this load happens to be minimum, and if we apply this particular minimum force, it will even the net deformation can also be contained, and the stresses reaching beyond the allowable limit can also be contained. Therefore the minimum value is to be chosen. Lower value of the load, that is P equal to 18 kilonewton, is to be considered. A punch. This is an interesting problem. A punch for making holes in the steel plates is shown. Assume that the punch having a diameter d equal to, this is the punch, and here it should be applied with a load, with a force, huge force, so that it will pierce through this plate and there is a hole created. Having a diameter of d equal to 20 millimeter, therefore the hole that is created will also be 20 millimeter in diameter, is used to punch a hole of 6 millimeter thick plate. This plate has a thickness of 6 millimeter. The cross section is also shown over here. This is the punch, and this is the diameter of the punch, and this is the load that is being applied. Okay, 100 kilonewton is applied, and it should be 100 kilonewton and 6 millimeter. And here this happens when the force is applied. There is this particular portion of the material, the plate will come out in the form of a disc, like this, creating a hole. Therefore the resistance will be developed. Okay, this is the applied load through the punch, and the resistance will be developed on the periphery opposing this particular load. Therefore this is none other than the shear stress. So if we stretch out this perimeter, so it acts along the perimeter or the periphery of this particular disc, and if you stretch out this, the length of this periphery happens to be pi d, and the thickness is 6 millimeter. Therefore the entire, if you unfold this periphery, unfold this disc, the surface area happens to be rectangular in nature, and if you fold it, it becomes a circle. Okay, this is the development. Okay, this is the development of a periphery. Okay, pi d into 6. So this is the resisting area over which the shear stress is developed, and we will apply this. Shear stress equal to shear force divided by resisting area. We never say area of cross section over here as far as shear is concerned. This is a very important point to note. So it is 100 into 1000 to make it Newton divided by the resisting area. Pi d is 20 millimeter and 6 is the thickness. This is pi d and this is thickness. So this becomes the area, resisting area. So from the shear force criterion, the shear stress that is being developed is 265.25 MPa. Therefore compressive stress in the punch is sigma force divided by area of cross section of the punch, because as far as punch is concerned, it becomes an axial stress. As far as the plate is concerned, it becomes a shear stress. So it is 100 into 1000 into 4. Okay, and this is pi d square by 4, because the diameter of the punch is 20 millimeter. Pi d square by 4 will go up, and this will give us 313.3 MPa. Therefore punch is subjected to more compressive stress than shear stress. Shear stress is low when compared to compressive stress experienced by the punch. 22. Okay, the 2-bar truss ABC shown in figure is supporting a plate, maybe a name plate. Determine the required cross-sectional area of the bar AB and the required diameter of the pin over here at the support C. This is the pin which runs through the heart of this particular rod, and here is also a pin, and there is a bar that is being held like this. Okay, this problem comes like a system. Okay, the pin at support C is under allowable stresses in tension and shear are 125 MPa. So this is permitted to experience an allowable stress of 120 MPa, which is tension naturally, and as far as this pin is concerned, it can experience a shear stress of around 45 MPa respectively. And this problem represents a system, a frame and a hanging. The hanging is held by two links, one over here and one over here, that are symmetrical, and you can notice over here it is 0.9, it is 0.9, and the weight of this particular hanging happens to be 5.4 kilonewton. Therefore it is pulling these links. Okay, and it is symmetrical, therefore this link is experiencing 2.7, that is 5.4 divided by 2, and this link is also experiencing 2.7. So now this entire board can be taken out, and we will write the free body diagram of this particular bar, and here there is a tension which goes along the axis of this particular bar, and we can calculate the angle. It is if this is theta, tan theta is opposite by adjacent. Opposite is 2 and adjacent is 3. 9 plus 0.9 plus 0.9 1.8, 1.8 plus 0.4 2.2, 2.2 plus 0.8, it becomes 3. So 2 by 3 becomes 0.67. So theta equal to tan inverse 0.67, that happens to be 33.82. This angle is 33.82, and there is a tension force, and this tension force is named as FBA, and it can be resolved into horizontal component and vertical component, and this is FBA cos 33.82 and this is FBA sin 33.82. As far as pin is concerned, it is experiencing horizontal reaction and vertical reaction, because a hinged support or a pin will never come down, therefore it will experience vertical reaction. It will never move horizontally, therefore it will also experience a horizontal reaction. It cannot move horizontally because of this particular component of this load or this force, and it cannot move vertically also because of this particular component. It can neither be pulled down nor be raised up because it will resist. Therefore the reaction will develop like this. We call it as vertical reaction at C, and we call it as horizontal reaction at C, and we will find out the resultant reaction of these two. It is the resultant reaction which is acting like a shear force through as far as this pin is concerned, and this particular component, the bar, is experiencing tension. Therefore this system becomes this system carries three unknowns: the tension, the vertical reaction, and the horizontal reaction. Therefore we need to apply the principles of equilibrium, wherein we will put up sigma fx equal to 0 to find out the horizontal reaction, and we will apply sigma fy equal to 0 to find the vertical reactions, and we will also apply sigma mc equal to 0, that is moment about C equal to 0. Thereby we will calculate HC, VC, and FBA. So that comes in the following steps. We'll carefully follow that. Sigma fx equal to 0 will only give us FBA cos 33.82, the horizontal component which is acting leftwards, should be equal to H, which is the horizontal reaction which is acting rightwards at the hinge. And with this we cannot calculate any unknown, and we need to take moment about C. And this particular equation corresponds to sigma mc equal to 0. MC being held as the moment center. Okay, and we will take the moment, and this is clockwise moment. This is clockwise moment. FBA sin 33.82 into 3, owing to the vertical component of the bar, the force in the bar, and this is the link force, the tensile force that is acting in the link, 2.7 into 2.6, and this is the other link, 2.7 into 0.8 equal to 0. So it will give us FBA equal to 5.5 kilonewton. So with the known FBA, it is possible for us to calculate what is the horizontal reaction, and we'll continue further. H happens to be the horizontal reaction at the pin, happens to be 4.57 kilonewton, and if we take sigma Fy equal to 0, V the vertical reaction at the pin, and FBA sin 33.82, the vertical component of the bar, the force acting in the bar, minus 2.7, the vertical the force, link force, the tensile force going down at the link, and minus 2.7, another link equal to 0. Therefore what we get is V. So at the link we can see VC HC, and the resultant can be calculated by taking the square root of the square of HC and square of VC. That's what which is being done over here, because we need to consider the resultant reaction as the shear force. So shear force or the resultant reaction happens to be 5.13 kilonewton. And if we continue further, sigma BA equal to FBA divided by A, and area of cross section is given because that is made out of a diameter. What is that? The area, yeah, the force is 5.5. Okay. The allowable stress is 125, and we are calculating the area, which happens to be 44 millimeter square. Therefore shear stress in the pin happens to be R in the pin, that is the shear force in the pin, divided by 2A, because the pin will be broken into 3 pieces if at all failure happens. Therefore 2 areas of cross section are participating, because pin is an example of double shear. So area of cross section is calculated, because the allowable stress in that is 45. Therefore we have calculated this. The force is 5.13, that's the resultant, into 1000, make it Newton, and this is 2 into 45 because it is double shear, and this is the allowable shear stress, which will give us 57 millimeter square. Therefore pi d square by 4 equal to 57. We will get the pin diameter to be 8.52 millimeter. Yeah. A solid steel bar of diameter D has a hole of diameter D hole 28 millimeter drilled through it. It is similar to the problem that we solved, but it comes with a little difference. Let us see. A steel pin passes through the hole. Here is the hole, and it passes through, and it serves as a support, and this particular rod is getting pulled with P, which is an axial tensile stress, and this is the diameter of this particular bar. And anyway, as far as pin is concerned, it is subjected to double shear, and as far as this rod is concerned, it is subjected to direct shear. Okay, when we consider this bar for direct tension or tensile stress, we need to consider this critical area where some of the materials of this bar is taken out due to drilling of the hole, and this is the area. So the effective area of cross section available as far as this bar is concerned is only this segmental portion and this segmental portion. Therefore the total area should be minused with this particular area, which is D1 into D2. Let us see what is the question. So tensile load of P 125 kilonewton acts on the bar if the yield stress in tension for the bar is 250 MPa with a factor of safety is 2. What is the minimum allowable diameter of the bar? Okay, we'll calculate that. So sigma equal to 125 into 1000 divided by A. Okay, 125 is load, and this is area of cross section. We have made it to Newton, and we get sigma to be 125 MPa. Yeah, and area is pi d1 square minus divided by 4 minus d1 into 28, because the diameter is given to us. Okay, d1 into 28, d1 into 28. Okay, yeah, 28 millimeter hole is drilled. So we get the effective area, this portion and this portion. So therefore area happens to be 0.7853 d1 square minus d1 into 28 upon simplification. Okay, upon simplification, so we will get this. So this is how it should be seen. So there is a full area, and here the hole goes something like this. Therefore this whole area is not at all available. The maximum area is available only at the diameter, only at the only if we take the section at the diameter over here, not somewhere over here, because here it is carved, and we have to take the section over exactly over here, because it is this cross section, which will give us the minimum area of cross section on minimum material that is available as far as this particular rod is concerned. Okay, and upon simplifying, we will substitute this with the allowable stress, and this is the load, and we will get a quadratic equation in D1, and when we simplify this, D1 happens to be 57.5 millimeter. Therefore, the diameter of the rod, okay, considering the allowable stress and considering the hole that is being created, happens to be 57.5 millimeter. A horizontal spacer bar like this of uniform cross section, therefore it is prismatic, fitted between two unyielding walls. Unyielding wall means they never get a dent, nor they will move leftwards or rightwards. Here this wall will also never move rightwards or leftwards. It is unyielding. Okay, it will never give away. Okay, it is 300 kilonewton. It is stone walled. Okay, it is some component is fixed between the walls are fixed. Okay, this is the configuration of the bar, and the question is, determine the reaction of the wall at B if loads on the bar are applied at intermediate points. So here is so this particular load is applied to this portion, and this particular load 150 kilonewton is applied to this portion, and the question is, determine the reaction at the wall. So this is pulling this way, this is also pulling this way, therefore the reaction should be like this. Yeah, reaction should be like this, and we don't know what kind of reaction exists over here, therefore we will put it tentatively like this, and the DLB, and this is an example once again for a principle of superposition. This is AB, this is C, and this is D. Yeah, we will write it clearly for the sake of clarity. This is C and this is C, this is D. And since there is no load over here and we will release the support, we will assume for a while that there is no support. We will release the support. Therefore there won't be any reaction, and therefore there is no force as far as dB is concerned. Therefore change in length of dB equal to 0. As far as CD is concerned, we have, so dB no force. As far as CD is concerned, there is 300 kilonewton. Therefore 300 kilonewton this way, it happens to be tensile in nature, and we will apply this and we will also get it ready. So DL by CD, DL of CD, change in length of CD portion is this. Okay, and change in length of AC, it is 300 plus 150, 450 kilonewton, and we have all applied over here. And as far as change in length in AC is concerned, it is the expression. And it is also going for elongation, this also going for elongation. And now we will apply the support, and support will be definitely offering a reaction like this. If the forces are tending to increase the length, this is trying to push it out so that there is no deformation over here, because walls will never yield. So RB into 1000 into 600 PL, because this 600 is the total length of the bar. Okay, 600 is total length of the bar, and this is RB. We are converting RB into Newton, okay, by multiplying it by 1000 by AE equal to the elongation of the portion, the second portion, the first portion and the second portion, and the last portion is 0 as we have computed. And if you simplify this, by substituting all the values, AE will get cancelled, because we will take it out as a common factor, 1 by AE, so AE will get cancelled. Okay, therefore in this problem there is no need to give us the value of A or value of E, so they will cancel away. So RB equal to 125 kilonewton, and if we apply the principle of equilibrium, we will have RA plus 150. So here it is assumed to be RA 150, that is RA towards right, 150 towards right, plus 300 towards right, minus 175, just now we have computed, will give us RA equal to 275 kilonewton. Okay, that is the thing. Even if you are taken wrongly, for the equilibrium, things will get adjusted and we will get the answer to be minus, and we will reverse the force. So had we taken this way, it would have given us a negative value. Okay, looking into negative value, we would have reversed the reaction in this way. Okay, a steel pad, the last question. Okay, we have come to the last question. A steel pad supporting heavy machinery rests on the floor 4 short hollow cast iron piers. Piers means supports. See figure. Okay, we will just remove this. Because it is copied from the problem has been copied from the book, and as far as the figure is concerned, of course it is solved over here only. Okay, right. Okay, we rest on the 4 hollow. There are 4 supports which are symmetrically placed for a platform. On this platform, heavy machinery is kept, something like this. It is a platform and there are 4 supports, 1 2 3 4. Fourth one is missing from the side because it is somewhere over here, and this is the machinery part, and it is symbolically shown as if the machinery is applying and coming with a heavy weight. Okay, the outer diameter of the pier is 100 millimeter and the wall thickness is 10 millimeter. So this is a hollow support, hollow pipe with outer diameter 100 millimeter and wall thickness 10 millimeter. Using a factor of safety of 3 with respect to the ultimate strength, determine the total load P that may be supported by the pad. So this is the total P which is applied, okay, due to the machine, and as soon as this load is applied, there will be P by 4, P by 4, P by 4. All the 4 supports will share the total load of P. And as far as the supports are considered, it will be like this. The section is like this. This is the outer diameter and this is the thickness. Therefore, the material is available only in the annular space because it is a hollow cylindrical support, let us say. And this is the total load. And we need to calculate what is this total load, keeping regard to the allowable stresses as far as the supports are concerned. Because the ultimate strength is given of this cast iron supports, it happens to be 300 MPa. We make use of the factor of safety and we will determine the working stress of this particular supports. So here it is. Safe stress in the cast iron pier equal to 300 by 3. 300 is the ultimate stress divided by 3 factor of safety, that will give us 100 MPa. Therefore these supports must be designed for 100 MPa. That's all. The area of cross section of the pier equal to pi by 4, the outer diameter square minus inner diameter square. The thickness is 10 millimeter. Therefore 100 minus 10 over here will give us inner diameter. So 100 square minus 80 square will give us an area of 2827.43 millimeter square. And if we apply the simple formula, P by 4, P by A. Here P is a function of this total load, therefore it is P by 4, the load borne by the individual support. So P by 4 divided by 2843 equal to 100 MPa, the allowable stress, so which will give us a P value of 1130.97 kilonewton. My respected viewers, with this we close this session, and we have clearly explained the concept of simple stress and simple strain by going through 25 problems in 3 tutorial sessions. So next tutorial will bring up the next advanced concepts of simple stress and strain. So until then, bye. If you have liked this video, kindly subscribe to my channel.